Hello and welcome to this fourth and final module in our mining engineering course. In this module, I'll take you through the key aspects related to underground mining activities. In this module, we will look at economic considerations in regard to underground mining, geological conditions suited to underground mining, the different operational and technical approaches used in underground mining, and important operational considerations including roof support, ventilation, safety, water management, and post-mining issues such as subsidence and closure. Let's start by looking at some of the economic considerations that are specific to underground mining. In Module 1, we took a look at the economic considerations for mining in general, and the principles we explored there are relevant here. However, per unit of rock excavated, underground mining tends to be more costly than surface mining operations, and this has consequences for the assessment of economic viability in underground mining. Some deposits that are uneconomical to mine using surface techniques are economical with underground mining methods, and vice versa. This is because every geological situation and every mine is different. There are many reasons why underground mining is so much more expensive than surface mining operations considered on a per unit basis. These include the presence of a rock roof or hanging wall, that is overlying rock, above the operations, and the necessity of managing the risks associated with working beneath it. This has a substantial impact on mining costs. The added complexity of getting what is excavated to the surface within a more highly constrained environment, and the management of other risks related to underground operations, such as water inrush, poor visibility, and poor air quality. The most basic economic consideration comes down to the ratio of the amount of ore that can be produced and the amount of worthless rock that must be moved in order to produce it. This is because the cost of moving worthless rock is lower for surface mining operations than it is for underground mining operations. So when there's a lot of worthless rock to move, surface mining operations are usually superior. However, if the ore body can be accessed through underground operations, removing little or no worthless rock in the process, then underground mining operations may end up being economically superior to surface mining, even for relatively shallow deposits. Another important economic consideration in underground mining is the extent of ore recovery, because it's very difficult to remove all of the ore in an underground mining operation. Invariably, as underground operations progress and excavations become larger, it becomes necessary to leave amounts of the ore body behind to support the roof in the form of pillars. In surface mining activities, it's generally possible to remove all of a resource, provided the miner, of course, is willing to dig a big enough hole. The selection of a mining method doesn't have to be exclusive. Sometimes it's most economical to mine a deposit using a combination of underground and surface mining techniques. Take, for example, a high-grade vertical or near vertical ore body, say a kilometre deep. Initially, as indicated by stage 1 in the drawing, it is most economical to dig directly into the top of the ore body and to take ore from the open pit. Mining can then follow the ore body downwards, but as we learned in Module 3, very high vertical walls become unstable and they must be battered back to a stable slope to ensure the pit walls don't collapse. As the pit gets deeper, stages 2, 3 and 4, the amount of worthless surrounding rock that must be removed to allow another level of ore body to be mined increases rapidly. At some point, the cost of widening the pit exceeds the value of the ore mined, and the open pit mining becomes uneconomical. This may be at a depth of several hundred metres. In the figure it is illustrated by the graph of profit versus mining stage, and it occurs after stage 4. If, however, there is still valuable ore at deeper levels, then it may be economical to switch underground mining methods and chase the ore body down to very deep levels. These can be mobilised from the base of the abandoned pit in order to reduce the underground transport distances. In the figure, this is represented by stages 5 to 11. Whilst the cost of mining at deeper levels increases, it remains profitable because there is little worthless rock to remove. As another example, let's consider a dipping seam of coal. Initially, where the coal seam comes to the surface, stage 1, it is most economical to dig directly onto the coal. Then, to mine more of the coal, a strip of overburden needs to be removed to expose some of the deeper coal, as was described in Module 3. This approach can continue repeatedly until the amount of overburden that must be removed to expose more coal becomes economically prohibitive, currently around 100 to 120 metres. This is shown in the figure in stage 5. Then mining must be abandoned, or else the mining method must switch to underground methods. Underground mining can then access the seam directly from the base of the high wall. Mining is more difficult and recovery is reduced, but the mining remains profitable since there is very little waste rock to remove. Not surprisingly, one of the principal tasks of the mining engineer is to design mining operations which extract the greatest amount of ore whilst minimising the amount of worthless rock that's handled. We're going to look at some of these aspects of underground mining in the topics that follow. A fundamental factor in determining the ratio of ore to waste rock produced is the size, shape and position of the ore body. This is generally related to the type of ore and to the geological origin of the ore body. In the next topic, we'll take a look at those geological situations and ore bodies that are best suited to underground mining techniques.